Good afternoon and welcome back to this final panel of the day, in which we will be discussing energy innovation from the perspective of several technology developers and providers. I once again want to thank Michael and Dan for bringing us all together for this year's TMA Blue Tech Week. I hope you found the presentations as interesting and informative as I have. Before we get started, I want to remind you to stick around after this panel to join us for the roundtable discussion. Bryson Robertson and I are hoping to encourage all of today's panelists and moderators to join us and to weigh in on some of the broad trends and developments that we're seeing in the marine energy sector. For this panel, each of our speakers will present some opening comments about their respective efforts, and we'll follow that up with some Q&A. Audience, please don't be shy and feel free to post questions that we'll get to at the end of the presentation. I have been informed that Lars Bjornsrud has been delayed in joining us today, so we're going to proceed without him for now, and hopefully he can join us as we proceed. So with that, I'll introduce Yi Chao, President and CEO of SeaTrek. Yi Chao, please proceed.
Thank you, Jason, for hosting this event. Thanks to TMA Blue Tech to host this exciting week of seminars and presentations. I can have my first slides, please. I will take this opportunity to introduce our energy harvesting system, how we use that ocean thermal energy to power autonomous profiling floats. Next slide, please. Many of you are familiar with the profiling float. It's autonomous, it's disposable, so you can deploy in the ocean. There are 4,000 of these Argo float in the ocean already live. You can see in the green dots shown on my right panel. So they are reporting data every 10 days, the profile of temperature, salinity down to 2,000 meters. It's a remarkable success in the last decade or two, replacing ships and to provide autonomous persistence presence in the ocean, really truly 24/7 and 365 to reduce the cost of data collection in the open ocean dramatically. What I'm talking about today, this energy bottleneck, and then try to extend the capability of this type of profiling floats to extend the lifetime of these floats, and at the same time to power more additional sensors in a sustainable way. The panel on the lower left show you the lifetime of these profiling floats is primarily powered by batteries, and the battery fully packed in the floats can last about 200 dives, after 200 dives, and then they essentially have to be replaced by a new one. As many of you know, it's more expensive to charter a boat to replace, to changing battery at sea. So basically every year you have to put in 1,000 more to replace the 1,000 dead ones. So the red dots show you the historically so-called dead floats in the last reporting position, 1,000 meters. Next slide. This is a kind of problem SeaTrek started about decades ago. We are looking at ocean thermal energy is unlimited, associated with temperature difference between the warm surface water and the cold water at depths. We developed this NASA Jet Propulsion Lab, this technology. We have patent granted 2011, is convert this thermal energy into electricity. So we're using phase change materials, this material in the solid state in the cold water. As you come to the surface, you warm the material, you melt the material from solid to liquid. That's convert into a volume expansion. And if you package them in the container, they were expand in volume, they will generate hydraulic pressure, they spin the motor, and then generate electricity. Next slide, please. So we have been going through this transition from academic research to commercial applications. The panel on the right showing two different configurations. Our energy harvesting system can be attached to the Argo float to provide essentially unlimited endurance and also scalable to power more sensors. So we have been going through a spin-off from Caltech, academic place, and then into a commercial product, and then continue to get government funding, raise private capital, try to scale the production in the commercial application. Next slide, please. So I'm really happy to announce this new project we just started, just recently funded by the Schmidt Family Foundation through Schmidt Marine Technology Partners in collaboration with Professor Larry Mayer, University of New Hampshire, and Professor David Sunwell at the Scripps Institute of Oceanography, is really to integrate these three relatively mature technology, the profiling float used by the Argo program, and then this energy harvesting, we have been tested with a variety of different environments. And then the single beam echo sounder also being used for decades. So we essentially integrate this into a profiling float at 1,000 meters. We can ping the seafloor and then measure the travel time to derive the depth of the bathymetry. And then you'll come to the surface and then report the data back through satellite communication. And at the same time, every time you surface, you go through this cold, warm temperature difference. You will harvest that into electricity and then recharge the battery and continue again to go to the mission. We hope to deploy this validation float off the coast of Hawaii, showing on the upper right corner. You can see is fully mapped near the coast of Hawaii because a lot of ship traffic, a lot of expeditions or research. So there will be a wonderful place to validate this new technology. And then really the goal is to map the gap of the global seafloor. The right lower panel showing off the coast of South America, Chile. You can see 80% of the ocean remain uncharted, and as hopefully to contribute this effort to a seabed 2030 is really try to fill as much gap as possible within this decade as a part of the Ocean Decade contribution. So I stop here, and then we can answer questions afterwards. Thank you very much.
Able. I am. Lars, are you prepared to present? I know you just got online.
Yep, I'm ready. I'm okay.
Wonderful. All right, with that, Lars Bjornsrud, Director of Marketing and Communications for Technic FMC. Welcome and take it away.
Thank you. You have my slides. There we are. So hi everyone, and thank you for the opportunity to speak about energy innovations at this year's BlueTech Week. Innovations and energy innovation, as well as other innovations, can take place at technology level and at product level. But there are also system level innovation. And Deep Purple, which I'm presenting today, is such a system level innovation. And in my presentation today, I will share with you what this system level innovation is. And you might wonder why we've called it Deep Purple. And some of you who are at a certain age, like me, know about the famous English rock band Deep Purple, but unfortunately there are no direct connections. Deep Purple involves the production of green hydrogen through the electrolysis of water powered by renewable energy. Hydrogen represents a crucial energy carrier for storage and transportation of energy, and we believe it will play a very important role to bring reliability, stability, and efficiency to renewable energy sources. Hydrogen can be used for decarbonization of heavy industries, transportation sectors, and converted to other zero-emission fuels. So Deep Purple is our initiative to innovate a complete zero-emission offshore energy system combining renewable energy with hydrogen. It can be configured to specific energy demand, including power generation, seawater treatment, electrolysis, hydrogen storage, and re-electrification. But then why the Deep Purple name? Well, deep refers to the environment Technique FMC operates in, deep waters and subsea. And when you burn hydrogen, it will emit a purple color. And purple is, by accident, also one of the colors in our company logo. But we actually made a connection with the band Deep Purple about 2 years ago at a festival here in Norway. One of the earlier band members, Jolene Turner, was playing at the festival, and we managed to meet up. And we told him about the project and asked actually for permission to use the name Deep Purple for our project. And he was very enthusiastic about our project and gave green light for us to use the Deep Purple name. Next slide, please. But first, a few words about Technip FMC. Our primary business is delivering projects, products, and services to the oil and gas industry. And we have a clear ambition to go beyond energies like oil and gas, providing solutions to the energy transition. Our world is offshore, subsea, and systems on platforms, but also systems for extraction of oil and gas on land. We're a $6.5 billion revenue company, employing about 20,000 people in 41 countries. Next slide, please. Going a little bit more into the details of our subsea business, this is where we find the experience and expertise to move beyond oil and gas. In subsea, we have products, technologies, and services to manage the flow of hydrocarbons coming from the reservoirs. And many of these products, technologies are also suited for offshore renewable business opportunities. Next slide, please. So we've been working with our Deep Purple concept for the past 5 years. And during the last 1 year, we've been in a system qualification phase. To qualify the system, we partner with energy companies like Swedish Vattenfall and Spanish Repsol, as well as technology providers like ABB, Nel, and others, and research organizations like SINTEF in Norway. Because bringing such complex energy system to market requires a high degree of collaboration. And this $10 million pilot project qualification program is supported by the Norwegian government through Innovation Norway. Next slide, please. So as mentioned initially, Deep Purple is our initiative to innovate a complete zero-emission offshore energy system, combining renewable energy with hydrogen. It can be configured to a specific energy demand, including power generation, seawater treatment, electrolysis, hydrogen storage, and re-electrification. Most of these building blocks are known technology. Putting them into a system used offshore is the innovation. In the case we're showing here, the renewable energy source is offshore floating wind. We delivered the first North Sea offshore floating wind farm to Equinor's Hive in Scotland a few years ago, and more of such offshore floating wind projects are planned. Other renewable energy sources could be tidal or wave, or in some cases we see a combination of these sources. A common characteristic of these renewable sources is that they are intermittent by nature. However, energy demand is fairly constant. Deep Purple is addressing this issue. One challenge is when the wind is not blowing. Another more positive challenge is when it's blowing way more than your demand is. Then what? Then you capture this surplus energy and store it, similar to how a hydropower-based energy system actually works. Next slide, please. So simply what we do is applying the known technology of electrolysis using the surplus electricity from the wind turbines when they produce more energy than demand, and then producing green hydrogen at a relatively low cost. Next slide, please. The hydrogen is compressed and stored in subsea tanks. In our current design, each of these subsea hydrogen storage modules can contain up to 12 tons of hydrogen, representing about 200 megawatt hours of electricity. If you compare this with the capacity in the battery, it represents the capacity of batteries of approximately 4,000 electric cars. Next slide, please. So when the electricity demand is higher than what the wind turbines can produce, the hydrogen is put into a fuel cell to produce electricity, also a known technology. Next slide, please. So let's move on and learn more about this new energy system. What we see through the windows of this control room is an opportunity that represents a total addressable market of about 6 gigawatts by 2030. And we see two main market segments, the first being offshore green hydrogen production and subsea infrastructure for coastal applications. Here, offshore hydrogen production will enable the harvesting of wind resources far from shore, where transport of electricity could be challenging. A hydrogen pipeline offers up to 10 times more capacity for energy transfer compared to a power cable, and our subsea storage system can be used to store large amounts of hydrogen close to end markets along the coastlines. The second is off-grid energy systems, delivering renewable and stable power to traditional energy installations offshore as well as remote islands. So let's move out and see more detail of this second segment. Next slide, please. So what we see here is the floating wind turbines producing electricity to a processing platform where electricity is distributed to end users. Hydrogen is produced, compressed, and stored subsea. Seawater is desalinated and cleaned, and fuel cells are burning hydrogen to produce electricity. What you saw in the control room is an advanced energy management system that monitors and controls the process to ensure stable electricity supply to end users. At the bottom, you see a typical graph showing the energy demand represented by the white line, electricity produced from the wind turbines in blue, both dark and light blue, and electricity produced from hydrogen in purple. At this particular time in the graph, we are in a situation where the wind turbines produce more electricity than demand, and this surplus energy, shown here as light blue, is used to produce and store hydrogen. So you see the hydrogen tanks are getting rather green, meaning they're getting very, very full. Next slide, please. As we move further out in time, we see that the wind turbines have stopped rotating and do not produce electricity. Hydrogen is then used to provide electricity to the end users. One of these end users could be an offshore oil and gas platform. Producing oil and gas emits large amount of CO2, and as an example, for Norway, this contributes to almost 30% of the country's total CO2 emission. Reducing this is fundamental for Norway to reach the requirements of the Paris Agreement. Providing renewable electricity to an oil platform by offshore floating wind only will reduce these emissions by 25 to 30%. By introducing deep purple and hydrogen into the equation, the reduction can be typically 80% and could go up to 100% reduction. Next slide, please. Here we've moved further out in time. There is still no wind, however, the hydrogen tanks still have capacity to produce electricity to meet demand. Next slide, please. Now we see that wind have started blowing again and is not entirely enough to meet demand, so hydrogen is required to produce additional electricity to meet this total demand. So here is a combination of electricity from hydrogen as well as from the wind turbines. Next slide, please. So here we're back in a good situation where the wind is providing the required electricity, and we can also produce hydrogen to fill up the tanks again. Providing stable renewable electricity to off-grid consumers like remote islands and offshore installations require a deep purple system. Using offshore floating wind only will not provide the stability required, and energy carriers like hydrogen is needed. The innovation in the deep purple system is to manage the complete off-grid energy system, optimizing the design of the facility with regard to the sizing of offshore floating wind farm, hydrogen storage, and processing capacities in order to meet energy demand at lowest cost. There are also innovations related to the subsea transportation and storage of pressurized hydrogen, including pipelines, connectors, and tanks. The energy management system also represents a new innovation. Next slide, please. Thank you for your attention.
Wonderful. Thank you. Thank you, Lars. And with that, Martin Edelin is up next. He's the Chief Executive Officer of Minesto. Martin, if you're ready, go ahead and proceed.
Thank you very much. It would have been much nicer to be in San Diego than Europe at this time of year. Nevertheless, it's good to be here, and I want to give you a little bit of an introduction to a tidal and ocean current energy technology that we've developed over many years, since 12 years back. And it's really a matter of bringing something to use to tackle about the same challenge as we heard Lars talking about, to get into net zero energy systems and balance the production with the demand. What we bring to the table is plannable and baseload type of generation. But I guess that we still, for tidal purposes, could have a good business relationship with Lars and his company on several applications. But what you see here is an historic picture for us. It's when we tow our power plant out to the production site this winter in the Faroe Islands to produce electricity to the grid for the first time with a kite-based tidal converter. So we are today one of very few companies that deliver tidal energy to a grid under a power purchase agreement. Minesto is also a listed company. So just to give you an idea, we are listed with a market cap around 3 billion US, which of course helps when you're bringing investments into the company and moving forward into scaling up the technology. Minesto is a company with 65 engineers today, 65 people, engineering heavy. And with that, I think we are one of the strongest engineering organizations in the world, focusing on bringing an ocean energy technology to life. And we have invested around $1 billion US in this, and a third of that is grants from the European Union, making us one of the largest contributors of investment funding from the EU as well. The technology, of course, I will show you in a minute, is still at an early stage. We're climbing the S-curve, but what is really good news for us after now almost a year of operations grid connected is that we have started the scale up into megawatt devices and commercialization. So you can say that on the innovation curve, the S-curve, we now reached a point where the performance and the cost structure, what we're doing, has sort of passed the point where we actually can move into commercial operations. I think you deserve to see how the technology works. If I can get the next slide, please. Here you see, I hope you can see the animation, how it moves. This is a system, you can look upon it as an underwater airplane tethered to the seabed, attached with a wire with cables in it as well. And then a wing structure that collects the energy and a lifting force is generated. So with a nice control system and rudders on board, we can fly this in a trajectory of an 8. And that means that we can sweep a large area of the sea, a large transection, collect energy not only from highly intense tidal currents, but also from lower intensity currents such as ocean currents and a much larger market of tidal currents. So it's built on high-speed rotation and low weight on the systems. Weight-wise, we're even a 10th or 20 times lighter than most ocean energy technologies in the wave and tidal sector. So this principle also makes it possible to reach far into this untapped energy source of tides and currents, the linear kinetic energy in the oceans. And of course, as we all know, the tides, they go by the clock, so we can also plan the production in a really, really good way. Which means, for instance, if we want to add energy storage to it, Lars and his colleagues will be able to offer something that is optimized in scale, and we will not lose anything because we know exactly when we produce and when we're not producing. The lightweight systems and the way of collecting energy, those principles, also put us in an extremely favorable position cost-wise. To be lightweight, to have really cheap installation procedures, brings us into a situation where after a few turns and twists of build out here, we will compete easily with offshore wind cost-wise. And I think that's one of the most boldest claims in our sector when it comes to delivering customer value. If we move into the next picture, I'll show you some action from real operations. Also some drone footage from a small village in the Faroe Islands. This is quayside operation. It's just a lorry crane moving this 100 kilowatt system out. We're using a small workboat. This scales well, so the megawatt device under production is also perfectly fine with exactly the same type of installation procedures. We're using a frame to get it into position, and this is an absolute key aspect of bringing marine energy into the commercial sphere, that you can touch your systems more frequently than you want, that you can inspect, that you can work with them, and also survive short service intervals. That's the nature of all immature technologies. Here you see a production mode from a GoPro camera on board of the system. We've had extremely good results performance-wise and are spot on our CFD estimates of how much energy would produce. So I think that's a little bit of action. If we move to the next, I'll show you the project portfolio where we are. We're working on 3 tidal projects, and shortly after we will see work in Florida and Taiwan on the ocean currents. Particularly the site off Lake Worth in Florida is really interesting for our technology. We may have to scale it up a little bit towards 2 to 3 megawatt units, which will help cost of energy even further, but to reach the right production context that's needed for the ocean currents that we've identified. Apart from that, the Faroe Islands, 100 megawatts to be installed. The UK, the biggest market in Europe, where we have our operations team in Wales. We're developing an 18 megawatt site, and we're collaborating with EDF in France on a site there. We have a strategic partnership with Schneider Electric to be able to bring the higher system level offer to the customers. And the utility in the Faroes, SEV, is a long-term partner for us to realize a 100% renewable energy system in the Faroes. So with that, I think I can show you my last slide here, which is a picture of the system that is now in production. We think it looks pretty cool. This is the Dragon class 1.2 megawatt system that will go into a grid-connected operation in the Faroe Islands towards the end of next year. And this is also the platform that we commercialize, both on the large-scale array park level, but we're also putting a 100 kilowatt device in for more, let's say, customized microgrid systems, and that goes into the water already first quarter next year. So with this, I hope I've given you a brief introduction to what we're doing at Minesto, and thank you very much.
Thank you, Martin. Very exciting technologies. Glad to see your company progressing.
Thank you.
And now for our final panelist, we have David Marchetti, Senior Director of Ocean Power Technologies. David, the floor is yours.
Thank you. Good afternoon, everyone. Thank you for including myself and our technology in Blue Tech Week. Today, I'll be telling you a little bit about our remote wave energy products and give you a little bit overview of where we stand in the development and some of our recent pilot projects that we've done. Next slide, please. For those of you not familiar with Ocean Power Technologies, we provide remote offshore power solutions, and we play in the markets listed there. So it's anywhere from oil and gas to defense and security, science and research, and communications. Next slide, please. Some quick facts about Ocean Power. We are a public company based in New Jersey. I am based in Houston, Texas myself. We've been in business since '94, and we have a small operation relatively to some of the other companies, around 50 people, and most of those are engineers and installation technicians. We also have sales offices in Houston, Texas, Indonesia, and the UK. Next slide, please. So a little bit overview on some of the products that we offer right now. Our PB3 is our flagship. It is a wave energy converter that basically converts wave energy into local electric power offshore. We also, for areas where there aren't a lot of wave activity, we offer a solar solution with a backup Stirling engine. And then we also offer a subsea battery for areas where they need immediate power. That subsea battery is focused on shallow water applications, 500 meters. And I'd like to tell you a little bit about some of the projects that we're working on right now and that we've done recently. This project was with a company called ENI, which is an oil company based in Italy. This project was to provide a buoy that would use wave energy to actually charge underwater vehicles. This one was for an unmanned platform, so they used the buoy to actually monitor the area. They charged an underwater vehicle so they would have eyes on the underwater activities. So that way they didn't have to worry about manned vessels. It reduced their carbon footprint and also gave them real-time data. One of the best things about our buoys is that it can send real-time data versus via a 4G network, Wi-Fi, or satellite, whatever the customer needs. Those buoys are rated, they generate power a lot smaller than the Monesto one. They generate power more in the 3 kilowatts. And for an example, in this area, even with small waves, we were generating 600 to 700 watts continuous. And it was a very successful project. They now want to move to the next step, which will be providing multiple buoys around the world. This was a pilot project from 2018 through 2020. Next slide, please. So another project that we did recently was for Premier Oil, which is now Harbor Energy. This was a little bit different application, and I wanted to show you some of the applications for our buoys. Our buoys, we consider them to be like a remote power generator. So if, like a construction site, except your construction site is out in the middle of nowhere. And we used this one again was using wave energy, but they used it for surveillance. They were doing decommissioning activities. They wanted something to reduce their carbon footprint. They typically had used vessels, fishing vessels, to use as guard vessels. Instead, they decided to use our buoy, and our buoys include, as you can see on the top there, radar. It includes infrared cameras and an AIS, so that then it can actually track vessel activity in the area. You can use it for monitoring illegal fishing, or you could use it for monitoring other illegal activities like smuggling. This is our project right now that we're doing off the coast of Chile, which is pretty exciting. It is for environmental monitoring, and it is for a company called Enel Green Power, which all you know is another renewable company. They are using it to check to see if anything in the water will change migration patterns, will change the water quality. And right now we're seeing that there is no effect by having our buoy there. And it's been deployed off the coast of Chile since May. Next slide, please. That's it. That's all I have for you today. I hope you enjoyed that. And if you need any more information, here is my contact information at the bottom here.
Wonderful. Thank you, David, for that presentation. And that concludes the 4 presentations we have for you today. And we're going to move into some question and answer. I've been keeping a few notes here, and we're looking for questions from the audience, so feel free to step up. Let me start perhaps with Lars. First of all, as a guitar player, as the Deep Purple thing, I just can't resist. Their signature song, of course, Smoke on the Water. We're going to have to help them come up with something a little bit more modern, reflecting the hydrogen economy and renewable energy. So let's put our heads together and come up with a new idea for Deep Purple. Lars, let's talk a little bit about your technology. How should we ask this? So the model that you presented there is an opportunity to produce and utilize the hydrogen in a centralized location at sea, with batteries, with the hydrogen functioning as a storage medium. So that makes a lot of sense. But do you think that hydrogen will be able to serve existing markets in the hydrogen markets, including, for example, refining and fertilizers, and perhaps for the growing markets around transportation and electricity production onshore.
Yes, we believe, as Sutton mentioned, the two segments. One being providing off-grid, stable off-grid renewable energy solutions, where hydrogen can be the battery that balances it, which I explained. But also, one of our projects that we're looking at is to replace coal in an industrial process with hydrogen. So we see also hydrogen as a factor into certain industrial processes. We know that a lot of the shipping companies and the companies providing main engines for large seagoing vessels are looking at ways to find other fuels than the bunker fuel that they're using today. And the shipping industry has also set very high targets for emission reductions, which require them to find alternative fuels. And ammonia is another sort of version of hydrogen that is a fuel that they're looking at finding ways so they can have a dual fuel engine that uses both diesel or bunker fuel as well as ammonia. So we see a lot of interest in using hydrogen into various industrial processes and into the transport sector primarily. But then we see the transport sector being primarily sort of heavy consumers like seagoing vessels, not so much the car industry. I think the Teslas of the world has found that batteries are very effective for cars and not necessarily hydrogen fuel cells are so effective.
Excellent, thank you. I know that in the European Marine Energy Center in Scotland, they're experimenting with using marine energy to produce hydrogen, powering local seagoing vessels, as well as perhaps some public transportation options in that island. So very exciting. Thank you. And clearly the hydrogen conversation is one that has expanded quickly over the last couple of years, and it's very interesting to see the synergy of hydrogen with the renewable sector. And I think we're all interested over the next decade to see how that plays out. Martin, let's turn to you for a moment. So the Minesto technology you presented, I think you said, was a 300 kilowatt machine. I'm curious, sort of physically speaking, is there how do you see the scaling of your technology? Is there an upper limit there, as we see in other marine energies, where it's a function, in most cases, for wave energy, for example, you simply can't keep making the thing ever larger. At some point, you're riding across the top of the wave crest. But with the Minesto technology, do you see an upper limit there?
Yes, it's the technology scales well. So where we are today is that we're building two 1.2 megawatt machines. And that's a 12 to 14 meter wingspan, depending on what energy density we have in the water. But what we're simulating and looking into for the ocean current sites is 3 megawatt machines. And then we're talking about a 20 meter wingspan. And a lot of the hydrodynamic properties actually improve when you scale it up a little bit. But as you clearly point out and understand here, we need more maneuvering space and space to turn the systems. So we're talking about larger water depths, maybe 200, 300, 400 meters of water depth to deploy those 3 megawatt systems. For the future, I don't think that we will not see the same extreme journey as with wind, where we talk now about 10, 15 megawatt units. But I'd say that there is a practical limit, perhaps around 5 megawatts moving forward. But there are also other aspects to the cost of energy relationship to scale here. For us, it's not just about growing. And for smaller water depths, we will talk about smaller systems. So a 100 kilowatt machine needs maybe 25 meters of water depth. And it would be impossible to fly the megawatt systems at 25 meters. They need 50 to 60 meters.
Excellent. Thank you. David, let's turn to you for a moment. So first of all, it's wonderful to see OPT's progress over the years. And it seems you've already successfully tapped into some of the existing market opportunities that we now refer to as the powering the blue economy, or PBE markets, versus going straight to utility scale. How do you see OPT's future? Are you focused exclusively on these PBE markets, or do you see the opportunity to use them to scale to utility or larger markets?
So for us, we did originally play in the utility market, and as one of the panelists mentioned, you get to a certain point where it's currently the technology is not cost effective compared to some of the other options. But what we are doing is we're commingling multiple, as we call, power takeoffs, which is the way you translate power from the waves into electric power. And so we are able to put those together and actually generate a large amount of power. We see the future is where we're actually about to put to power all electric trees. If you put a few of our buoys together, it's actually enough to power an all electric tree on the seafloor, which I'm sure Lars is very aware of. And so we see more and more demand for that. And we also see that there's some other applications. I didn't talk much about it, but we see a real demand for our technology for defense. And for like port security, where you're able to use our surveillance equipment and reduce the number of manned interventions. Then you don't put crews at harm. You can actually put our buoys out there to do surveillance in the middle of the night, 24 hours a day. And so I think what we see is being able to, the key growth area for us is to being able to get the buoys, the installation in faster and less expensive. In fact, we have some projects that we're working on where you can actually remotely install buoys out of the back of military vehicles and ships and things like that. So that's where we see a big growth area. I don't see us growing in utility scale at this point, although I will say we are doing a Department of Energy project right now, interestingly enough, to scale up the buoy. So as Martin said, there's a certain size that we can keep. The buoy we have now specifically to fit in a 40-foot container so that it could be shipped very easily around the world. But we are now going to the next level. So ours is rated nameplates around 3 kilowatts. We're now developing one that's somewhere between 15 and 25 kilowatts. So not as large as what Martin has, but it's needed for certain applications.
Yeah, excellent. Well, anyone who has worked in the marine renewable sector long enough knows the history of some of the first companies that attempted to move to utility scale as quickly as possible, and there were obviously a lot of issues that it's hard to foresee, especially if you don't take an iterative process with your technology development. And I'm very encouraged by the powering blue economy markets that have provided some sectors for companies to operate today and develop some cash flow. And continue to build experience with their technologies and improve them over time. And it does make sense that that might provide an excellent pathway to grow the technologies, to scale the technologies, and to one day be able to compete more directly with some of the other more well-established renewable technologies that are already online and coming online. Yi, let's turn to you for a moment. There's obviously one of the most important powering the blue economy sectors is the ocean observation. I think for a lot of folks it was an eye-opener to see the amount of effort and investment that's made into data collection around the world. It's an enormous market, and your company is one that I think is on the cutting edge of tapping into that and providing some significant benefits. I'm curious to what extent you've seen some advantages in driving the market for these new technologies, being driven by any kind of government policies or preferences in terms of using these technologies moving forward for their, like for example, NOAA's efforts on data collection. So have you worked with NOAA specifically or any other governmental agencies that have provided some opportunities for you to deploy and use your technology?
Yeah, we have been working with a number of different government agencies in the U.S. and start with the technology was developed at NASA, funded by the seed effort funded by NASA, and then eventually move into the DoD, the Office of Naval Research, for some of the military requirements and drivers. And then also we have worked with NOAA as well. Go back to the power of the blue economy, ocean observing. I think as we move away from the great power from some of the colleague speakers, talk about the big power generation to a more niche market, and you have a different type of challenges. You have very diverse customer base and even the market sectors. So it does require a number of different approaches. And David made a good case study, the buoys to power the underwater charging stations. There's a tremendous amount of surface vehicles being developed powered by solar and waves and winds. And then we are tapping along the ocean thermal in the interior. And there's because of diverse market, you need a diverse approaches and to address this very kind of fragmented, if you want to call it, the different demands.
Thank you. So let's move from sort of company-specific questions to some questions and observations about energy innovation in general. All of you are energy innovators in the green economy and the blue economy. And over the last few years, there's clearly been an enhanced focus on improving our operations at sea, decarbonizing those efforts, and generally reducing our impacts on the ocean and improving our understanding of the ocean and its processes. So, regarding these, the innovation aspect of your day jobs, let's talk about that a little bit. So, for example, perhaps some of you may have opinions on whether innovation in the blue economy or with clean energy in general is exceeding or lagging behind innovation, say the traditional or conventional energy sectors. Feel free, anyone who wants to weigh in on that, just go ahead. Go ahead.
Yeah, we're obviously lagging. I mean, there are not even 100 megawatts of, if you're not counting wind, which is not ocean energy the way I see it. I think wind has a lot of merits, but if you want to collect energy from the oceans, I mean, that's a sector where there is a natural resource that is basically untapped today. And I think that's a challenge for this sector, because we are compared with much more mature energy sources. And I still think that the net zero vision will need complementary energy generation. Even if Lars will take us far with compensating for the lack of predictability and matching demand with supply, I think we may even benefit more from those solutions because we have a very, let's say, easy to analyze context. We would know exactly how to scale and dimension storage to what we're doing because it's predictable. So there are a lot of reasons why we need to do better and do more in pushing ocean energy quicker. But we are lagging, and there's been a lot of different technologies with tidal, with wave, that has not delivered over the years. So we just have to be clear that we need to be much better and move faster than we've done historically. And I think that what several of the companies represent here, Lars with enabling technologies, that will help. I mean, C-Trek and Professor Chow, that's something that makes it more cost effective to learn about the ocean. And we need to learn even more about how those natural resources really behave. And I also think that with David's solutions there, with already in a commercial mode, with a lot of experience of operating at sea and also finding niche applications. I mean, if you combine those things with some brave candidates to be, let's say, dominant design solutions for this, we can give the world up to 10-15% of the global energy need from those natural resources. And I don't think we can afford to sort of leave that behind. So that's my my bold declaration as input to this. Thank you.
Thank you, Martin. Anyone else want to weigh in on that question?
Yeah, I can echo that, Martin. I think it's I'm also very impatient. I think it's we need to accelerate these innovations. The world needs clean energy, and it needs it fast. But at the same time, in the ocean space, we need to have respect and be mindful about the life in the ocean space, which we're sort of competing with. So understanding that is fundamental. We have to hurry up, but we have to do it carefully and be mindful of others sort of having their life in the ocean space. But there is a duality here, because we're also competing with innovations within traditional oil and gas, and there will be still innovations within oil and gas, and they often have a very clear demand because there is a market immediately for those innovations. The timing is a little bit slower for the renewable energy solutions, unfortunately. So that's one of my frustrations. I think we need to prioritize much more efforts into the renewable energy innovations in order to take the steps we need to take in order to manage the energy transition much faster.
Thank you.
Well said by Martin. The only thing I want to add, this is a good timing, and there's a tremendous increase of awareness from the society, and this is the ocean of decades, and then there's a significant momentum being built up. But starting this year, the ocean of a decade of development sustainability. So I think there's a momentum. It's up to us to step up and to meet those challenges.
Yes. So I was going to ask you whether some of the policies that have been developed over the past few years to address climate change, how those have helped you or affected your respective businesses and technology development. But I want to alter that a little bit and ask, which policies are still out there that are adversely affecting your ability to proceed as companies, as technology developers? Are there still lingering policies or basic operating procedures with financing or with government, with regulation that are impeding your efforts?
How many hours do we have?
Point six.
Not to joke. I mean, there are obviously a lot of policies now that are favorable and that support this transition. And I think that's the first thing to say. It is that we are slowly getting awake and alive here to make this transition. So it's a lot up to us also to offer solutions policy-wise to what we need. But I think there is one area, the classic area of environmental permitting, that we need to look seriously into. We need to protect the local environment, the marine life, very important. But at the same time, climate change is threatening that local marine life. So I think we need to find more clever ways of quickly getting experimental installations out, small-scale installations, and study and learn from them instead of having to provide evidence before they are installed. That is one of the factors that creates unnecessary risk to already risky new technologies and slow down projects. And I think that's an area where policymakers can do more short term. So that's my wish list, if I can have one item on it.
I agree. I'll add to that is that we've typically any new technology, whether it's been wind or ocean power, anything on the surface, we find that people don't want that in their neighborhood. They need the power. It's like anything. Nobody wants an oil refinery in their neighborhood. Nobody wants to see wind turbines. We have been. It took us a year to get the permit to do off Chile, just because there was nothing else in the water. It was a fishing village, nothing there. And we finally had to, as you mentioned, Martin, we had to make the extra effort to go down there, meet with the locals, and explain to them what was going on. And that's why we have so many sensors hanging off of our buoy, is they want to make sure that even our buoy will not change the pristine conditions. And so I think if you work with them, I find from our business, it's more the communities than it is the government regulators. We've had a lot of support from Department of Energy in the U.S. and other entities that want to try renewable energy, but it's really how do you educate the public and how do you work with them to address their concerns and ensure them that we want to be as successful as them, and we do not want to change migration patterns. We don't want to change the quality of their life, but we've worked extra hard to try and do that.
So in my area, for the niche market, and then for us, adapting new technology certainly is challenging, but particular renewable solutions and then reducing costs is probably one of the challenge we are facing. To have the right policy doesn't have to be subsidizing the energy costs, but even encouraging the use of renewables and then protect our environments and then being clean and sustainable. That would be tremendous help for the industry, particularly for startup companies.
Just to add a little bit, I agree we need to pilot, we need to test, and we need to learn, and we need to scale, and that needs to be incentivized. So we need a regime so you incentivize those kind of activities, and we see within the EU, for instance, there are incentives in order to do that. There's also a need for a system to punish those who pollute. There has to be a global way of doing that, otherwise it won't work. So you have to have a global system for CO2 pricing, for instance. Otherwise it's very hard to get this moving. So these two things together, I think is important.
Lars, I'm glad you brought that up. The one of our biggest challenges, I think, in the renewable sector is the inertia of the incumbent sectors. We have not yet disincentivized the status quo. We're doing our best to incentivize these new emerging technologies, but it's a difficult climb uphill, especially with the costs associated with building and deploying some of these machines in the ocean environment. And David and Martin, to your point around the regulatory environment here in Oregon, we've in process of constructing the PAC wave energy test site off of Newport, Oregon. Construction has begun, but that was about a 6-year permitting process to get the permits to build a test site. So, of course, our hope is that good work and hard work will have some long-term benefits to anyone who wants to move forward with the project, having answered perhaps many questions around what's required around monitoring and mitigation. But we'll see how that plays out. But it does speak to some of the challenges. In the final, minute and a half here, let's talk about money. What's changed, if anything, for your access to capital to help develop your emerging technologies? And if you can quickly try to get through that, we'll finish here in about 1 minute.
Yeah, if I start, I can say that the access to capital today, if you want to build projects and scale projects, is huge. The challenge is to find the capital for your first scale-up project. But I also think that if you look at the really big players, the project developers in the world today, it's they are moving into this to learn and to sort of enter into new areas. So I'd say access to capital has never been more positive in that sense. And it also helps when guys like Lars and Technip FMC, when those guys come in and provide enabling technologies. I mean, if Deep Purple can substitute AC/DC cabling, I mean, that will expand our market, and there will be supporting technologies that gives even further strength to what we're doing. Sorry for that one. I couldn't help myself.
That's a fantastic pun. It's a great way to end today's presentation. Deep Purple and AC/DC. Here's to rock and roll. All right, gentlemen, thank you all so much. Excellent presentations today. And I would remind everyone, please stick around in just a few minutes. We're going to start a roundtable and back out a little bit and see what we can take away from today's presentations. Thank you all very much.
Thank you.
Thank you.
Bye.